Hello, everyone joining us around the world, and welcome to the Distinguished Lecturer webinar series. Before we go any further, my name is Carrie Cosby, and I'm the Chapters Manager here at the IEEE Computer Society. I oversee our more than 500 professional and student chapters around the world and manage our Distinguished Visitors Program. Before we get started, I'd like to get a couple of housekeeping tasks out of the way. First of all, I'd like to remind all of you that we are currently accepting nominations for new distinguished visitors, and you can see our website to submit your nomination or a nomination for somebody else. We are looking for great people who are looking to share their experience and their ideas with their colleagues. I'd like to say that you can ask your questions in the Q&A panel. Dr. Kalefi will answer as many questions as he can following the presentation. When you're writing your questions, please make certain that if it's regarding a specific slide, you indicate what slide that might be, as these questions will come at the end of the presentation. The webinar is being recorded and will be made available after the webinar is finished. Today's discussion is the rise of quantum internet. I'd like to introduce the scholars that have made this presentation possible. First, I'd like to introduce Angela Sara Cacciaporti. She's a faculty member at the University of Naples Federico II, Italy. Since July 2018, she held the national habilitation as full professor in telecommunications engineering. Currently, Angela Sara serves as area editor for the IEEE Communications Letters and as editor and associate editor for the journal IEEE Transactions on Communications, IEEE Transactions on Wireless Communications, IEEE Transactions on Quantum Engineering, and IEEE Open Journal on Communications of Communication Society. In 2016, she was appointed member of the IEEE ComSoc Young Professionals Standing Committee. Since 2017, she's been elected treasurer of the IEEE Women in Engineering Affinity Group and the IEEE Italy section. Since 2018, she's been appointed as the publicity chair of the IEEE ComSoc Women in Communication Engineering Standing Committee, and then in 2020 as vice chair of WICE. Marcelo Kalefi is the DIETI department with the DIETI department at the University of Naples of Federico II and with the National Laboratory of Multimedia Communications. The National Inter-University Consortium for Telecommunications. From 2010 to 2011, he was with the Broadband Wireless Network Laboratory at the Georgia Institute of Technology and with the Nano Networking Center in Catalonia at the Universitat Politecnica de Catalunya as visiting researcher. Since July 2018, he's held the Italian national habilitation as full professor in telecommunications engineering. His work appeared in several premier IEEE transactions and journals, and he received multiple awards. Currently, he serves as editor and associate technical editor for the IEEE Transactions on Quantum Engineering, the IEEE Communications Magazine, and the IEEE Communications Letters. He's served as chair and TPC chair and TPC member for several premier IEEE conferences. In 2017, he was appointed distinguished visitor for the IEEE Computer Society, and in 2019, he was appointed member of the IEEE New Initiatives Committee for the IEEE Board of Directors. Dr. Kalefi, I'd like to pass the floor to you now.
Hi to everyone. I was wondering, Carrie, should we play the video or not?
No, I've skipped on that video.
Okay, great. Okay, thanks to everyone for being here, and we will try to see our latest journey in the topic, which is quantum internet. Let me share the screen. Okay. Carrie, can you confirm me that the screen sharing is working?
I see your screen has just come up. It should be coming to our audience in just a moment. Yes, it's now come up on our audience, so we're good.
Okay, so the presentation will be arranged in these three main sections. An overview about quantum technologies. First slide, okay, you should see the pointer now. An overview about quantum technologies and the reasons why quantum internet is becoming mainstream topic. A very short introduction to the quantum mechanics, meaning to the differences underlying the quantum internet. Internet is a challenging task, and why designing a quantum internet can provide undiscovered capabilities which are not present in the current internet. And then we will close the presentation with a recent Twitter from a person which revolutionized the quantum computing field, which is Sher. So let's start with the quantum technologies overview, and we will address these three main topics. Players, who is working now on quantum technologies? Market, meaning which markets and which business models may be or will be revolutionized by the quantum technologies revolution. And finally, we will have a small focus on the Europe situation. So players, here you can see the current players. We should say that I'm seeing that there are already some questions, but I think that we will go to the questions later. So you can see from this slide that IBM and probably Alibaba are the most active one in terms of quantum technologies revolution, but there are new players coming in the field every month or something like that. And also in terms of quantum communications, quantum technologies, we cannot mention the quantum satellite experiment missions conducted by China, which was on all the news and the newspapers a couple of years ago. So why this interest, with this broad interest among all these players? Well, these are the numbers, the figures. So the latest forecast expects a market for quantum computing of more than 10 billion by 2024, with half of the market for cloud solution. And not only you have these big numbers in terms of market, but you can see also the number of patents. Here, I want to point out that the patents refer to a period before 2019. You can see how China was playing the leader, was playing as leader for quantum communications. But I should point out that in the last month, US with the quantum initiative is trying to fill the gap by funding several research centers around the nation to build this quantum internet, and you can check the news and all the newspapers and articles about it. So I want just to say that this figure is not accurate when it comes to 2020. And this is the number of investments, private investments, and you can see that, of course, we have Rigetti, which is a big player, D-Wave in the States, more focusing on the computing aspects, and we have Vidicantic in Europe, which raised $75 million for developing quantum communication. Okay, so this is the data, but what about funding? This was the estimated technology, quantum technology expenses in terms of research in 2015. And you can see that China, Europe, and United States are somehow spending the same amount of money. But since 2015, we have several new funding projects. Europeans start first with 1 billion quantum flagship in 2018. Then in 2019, we had the announcement of a similar program in US, so the 1.25 billion National Quantum Initiative. And Europe and some states in Europe, like Germany, is even increasing this amount of money with national investment. So there is a huge interest from both companies, as you see in the player slide, and nations to invest in quantum technology. With Europe, as we said, we have the quantum flagship, which started in 2017, 2018 as generalistic funding program for quantum technologies, but eventually last year evolved in a more specific focus. Specifically, the final goal of the quantum flagship is the quantum internet. So in Europe, it has been recognized that the final goal of this $1 billion investment should be what they call in the Quantum Manifesto the quantum web, but for telecommunication engineers, it's clear that they refer to the quantum internet because they define distributed quantum computers and quantum sensors interconnected via quantum communication network, which is the quantum equivalent of the current classical internet. So this is for in terms of market. Now, we saw the quantum technologies. Let's move to the quantum internet. And the first thing that we need to understand in terms of quantum internet are the differences between classical and quantum internet. I apologize for the next 20 slides that they will be somehow technical. We try to keep the technical details as simpler as possible, but it's important to understand why a quantum network differs from a classical network, to understand why a quantum bit is something completely different from a classical bit. I want to point out that some people from the photonic community can think that since usually qubits are transmitted with photons, and also bits are transmitted with photons in classical fiber lines, these people with this background can think that there is not so much difficulty in switching from classical to quantum communication. At the end of this part, I will try to focus on why designing a quantum internet is such a challenging task. So we have the bit, the classical bit, which can assume just two possible values, 0 and 1. And usually, when you introduce someone to the quantum mechanics or the quantum information theory, you start saying incorrectly that a qubit can be 0, 1, or both at the same time. This both at the same time expression is not accurate from a quantum mechanics perspective, but gives an idea, a feeling to someone new to the field that quantum bit is something that you cannot grasp with intuition. We have the intuition since our classes, undergraduate classes, of a bit, but it's very hard to grasp the intuition behind a qubit. There is another way of introducing a qubit, which is like flipping a coin. Also, this expression is incorrect. Why? Well, the reason is the following. When you flip a coin, if you know all the variables, all the initial momentum, the direction of the coin, the speed, you can derive the output. So flipping a coin is not something random by itself, but it's random because you don't have knowledge about what is describing this experiment. With a qubit, you don't have randomness by ignorance, but you have randomness by definition. So let's try to give a more formal definition of a quantum bit. You have a bit which can be 0 and 1. Then you have a qubit. We can assign two basic states to the qubit. We can call it S an orthogonal S or 0 and 1. What is important is the following. If you have two valid states, any linear combination of these valid states is a valid state as well. So if you have S and orthogonal S as valid states, any linear combination, you have written here a linear combination with parameter alpha 0 and alpha 1, is a valid state. Since alpha 0 and alpha 1 are continuous values, you have that a qubit can store infinite values. Usually, we as information technologies engineer, we don't care so much about the physical state underlying a qubit, and we use the usual 0 and 1 state, classical state. So if I have 0 and 1, which are valid standard basis, I can have any linear combination of 0 and 1. And two more very popular states are the plus and minus state. Another intimidating aspect of the quantum mechanics is that usually quantum mechanics is a notation which is unconventional for engineers, which is the bracket notation. Now, I understand that during this talk, it's not easy to catch this, but bracket notations, despite their unusual notation, they are simply metrics. So, if you had an introduction to matrix multiplication during your undergraduate classes, you have all the basics that you need to understand quantum mechanics. Okay, this slide mentioned the block sphere. The block sphere is a way to visualize a quantum bit. And in the block sphere, you have the two basic states. Let's call it classical states, even if it's not correct, 0 and 1, which are depicted as north and south poles. And every point in the surface of the sphere is a valid quantum state. Indeed, also the interior of the sphere is a valid state under certain hypotheses. So the block sphere is a convenient tool to visualize the value of a qubit in a three-dimensional space. Okay, now what I want with this slide to stress out is the following. Quantum technologies, mastering quantum technologies requires, from the physical perspective, mastering the physics underlying the quantum mechanics aspect. From the information technology perspective, indeed, with the qubit, you don't need to master the physics behind the hardware, and you can easily grasp quantum mechanics by abstracting from the particulars. Particulars which are shown here. For example, you can implement a qubit with a superconducting circuit, with a natural or artificial atom, with several different hardware technologies. Each technology has its pros and cons, but the important thing is that quantum information allows you to represent a qubit regardless of the underlying physics technology. So, we have the classical bit, which is just 0 or 1. And you have the qubit, which can be 0, 1, or both. Now, why is so important the qubit notion? Why do we need, as engineers, to start understanding quantum information and, above everything, start exploiting the power of quantum information? Well, this is the easiest example to start understanding the power of quantum information applied to computing. So let's suppose that you have a task. The task is the following. You need to uncover one of these 4 cards, which are randomly shifted. And when you find the heart of the ace of hearts, you win. So this is a classical computational problem. And if you ask to a programmer to solve this problem, you will find that solving this problem on a classical computer requires an average 2-point-something turns. So the computational complexity of the problem, how hard is the problem when the number of cards grows from 4 to very large number, is polynomial but linear in terms of n. When it comes to quantum computing, you can solve the same problem with less than 2 turns. And again, it's not easy to understand how is it possible to just turn 1.4 cards and solve the problem. And the reason is the following. We, as human beings, have intuition just in terms of classical nature, because this is the reality that we experience. Quantum mechanics is a reality that we don't experience every day, so it's very hard to grasp the quantum mechanics with intuition. But indeed, as I will point out during the presentation, with just few concepts and with just few very simple understanding of matrix multiplication and this kind of backgrounds, you can understand quantum information very well. So when we pass from 1 qubit to multiple qubits, what we have is the exponential scaling of the space that we can describe. So for example, we say that a qubit is a linear combination of 2 basis states. 2-qubit system is a linear combination of 4 basis states, which we call 0, 0, 0, 1, 1, 0, 1, 1. And then you have the n qubit system, which is a superposition of all 2 power n basic states. Now, without the aiming of being very precise here, we can say that this exponential scaling is one of the reasons of the power of quantum computation. The other reason is entanglement, and we will see later. So, as you increase the number of qubits within your quantum computer, you are increasing the space of the solution that you can explore at once. Again, this explore at once is not a formal definition. It's just something to give an intuition of what is going within the quantum computer. So we can say that one fundamental property of quantum computation, quantum communications, quantum information is the following. The more you add qubits, the larger is the power of your technology. And the growth with the number of qubits is not linear, is exponential. That's the reason why you may have heard in the newspapers that Google achieved quantum supremacy with 50 qubits. Because there were 53 qubits, but never mind. 50 qubits, the power of 50 qubits must be interpreted as the power of 2 power 50, which is something that grows very large, very quickly as you add more qubits. So if you add just 1 qubit, one ideal qubit in a quantum computer, the power of that computer doubles. And if you add 10 qubits to that computer, the power of the computer, of the resulting computer, of the enlarged computer, increase of a factor times 1,000. I want to give some more slides and then have a short break for question and answer. So we have a qubit, which is something that can store much more information than a classical bit. This is the good aspect. But what about measuring this qubit? Well, the bad news is the following. Every time that you measure a qubit, you either obtain 0 or 1. So Put in another way, every time you measure a qubit, you get one bit of information. So the measurement process is something that destroys the quantum information. It collapses the quantum information into classical information. So measurement is something to avoid as much as possible, because every time you measure a qubit, you destroy part of the information stored in the qubit. And this problem with the measurement, which is a postulate of the quantum mechanics, is shown by this picture in which a boss asks to his employee how is going the quantum computing project. And the guy is saying, well, it's in a superposition of not yet started and finished. And when the boss asks the employee, can I check the status of your project? He says it's a tricky question because checking meaning measure something, and when you measure something in the quantum world, you destroy it. And with this slide, we don't have time in this short 1 hour talk. I just want to point out that you can't perform quantum experiments, not simulation, experiments with a quantum processor nowadays, for example, using the IBM co-experience. So IBM is not the only unique tech giant providing access to quantum processors, but it was the first. And nowadays, you can experiment with IBM quantum processors from 5 up to 14 qubits. And here, what I'm doing, what I did with this small example was creating a superposition of 0 and 1 state within the quantum processor. So I create a qubit which was simultaneously 0 and 1. And this is the math behind the superposition. As I told you, all you need is multiplying matrix. Here you have a matrix that represents the Hadamard gate. And here you have the multiplication, and what you obtain is a perfect superposition of 0 and 1. But what I want to stress here is that these are the experimental results. So I create the superposition of 0 and 1. I measured it, and when I measure, I didn't obtain the original results, but I just obtained a classical result. So the measurement process destroyed the quantum information, first aspect. Second aspect, important, the result is not perfect, meaning I didn't obtain 50% of probability of measuring 0 and the 50% of probability of measuring 1. Why? Due to the errors which are intrinsic in quantum information. And I will go back to the error here when I will talk about the current. So we have superposition, and we have the measurement postulate, which says that every time that you measure a qubit, you destroy quantum information. And then that's the superposition experiment. And then you have the second guessed reason for computing power, which is the entanglement. So, as we said before, when you have 2 qubits, you can have 4 basis states. With these slides, I tried to visually give you the idea that 0, 0 as basic states means that the first qubit, which I denote with A, is in state 0. And the second qubit, which I denoted with B, red, is in state 0. So when I say 0, 1, I mean qubit A is in state 0, and qubit B in state 1. So of course, the possibilities are 4, 0, 0, 0, 1, 1, 0, 1, 1. Now, any linear combination of these 4 basis states is a valid state. thanks to the superposition principle. Now, when we have a 2-qubit system, we can measure it, and we can decide to measure both the qubits. For example, alpha 00 denotes the probability of measuring 2 qubits in the state, both in the state 0, or I can choose to measure just one of the 2 qubits. Measuring one of 2 qubits is a key ingredient to understand entanglement. Now, in the classical world, the whole body is the sum of the parts, and we usually express this analytically in terms of tensor product. So what I'm saying here is the following. A 2-qubit system denoted with phi is the product of the first qubit tensor product and the second qubit. Now, this is something that we are used to understand it, because this is how the classical world works. Now, can we say that this works always in the quantum mechanics? Let's consider this state, the state 00 plus 01. With the colors, I stress out which is the value of the first qubit, which is always 0 for both these valid states, and the value of the second qubit. Intuitively, we can rewrite phi as the linear combination of the first qubit being in state 0, tensor product, the second qubit being in state 0 plus 1. This state, which you see here, is a separable state. So it's not an entangled state. When it comes to entanglement, this is a classical example of entanglement, you have this special state. 00 plus 11 is usually considered the classical example for an entangled state. Why? Because there is no possibility to write this state as the tensor product of 2 individual single qubit states. And if you look at the demonstration is very easy, okay? But let's skip the demonstration, and let's assume that we have separable states and we have entangled states. And entangled states like this are not separable. This is the formal definition. Now, why entangled states are important and why are so important from the communication perspective? Okay, so here I'm summarizing what I said by voice. We have separable and non-separable states. When it comes to non-separable states, those states are defined as entangled states. And they are also called Bell states when they are maximally entangled. Now, why entanglement is so important and why is so hard concept to bring Einstein to define entanglement as Spooky action? Here, the Spooky is translated by German, and you should understand spooking not in the sense of weird behavior, but more in the sense of divine behavior. Well, for this, let's suppose that we measure one of the 2 qubits forming an entangled pair. So let's suppose that we measure the first qubit. When we measure the first qubit, what we have is that the first qubit, which is a superposition of 2 valid states, 0 and 1, by measurement collapse. So what's happening is the following, that you have 2 qubits which are random variables from a state perspective, but once you measure one of the 2 qubits, the second qubit instantaneously collapses. So this is what is usually informally defined as instantaneous action at distance. And this action is faster than light. Okay? So, entanglement represents special states. States that are not separable. States that cannot be described individually, but they can be described only as a whole. Once you measure one of the particles forming an entangled state, the second particle is affected as well. And this affection, this change, is instantaneously. Now, do you have any question about entanglement, or can I keep going?
There are a few questions. Actually, there's one at the moment sitting in our question and answers. And that question is, for a qubit with a number of states d, the scaling is then d to the power of n, correct?
Yes, it is correct. And this is a critical point, which is bringing researchers trying to move from a qubit system to a qubit or a qubit system, because the larger becomes your basic state. So if you move from two basic states, 0, 1, to three basic states, 0, 1, and 2, or whatever you want to call the basic states, the power or the dimension of your space state grows exponentially. But when we will come to the current, I will make a comment on why qubit or qubit are hard to explore with the current technology. Okay.
One more coming in, if you have a moment for that. This person says, is there anything ternary like binary?
Yes. Well, indeed, when it comes to the hardware underlying a qubit, usually the hardware, the device which implements the qubit is not a two-level system. Usually, or most of the hardware is an n-level system where you use just the first two levels. So the problem with using more levels, so moving from binary to ternary quantum state, is not a hardware problem, because nature by itself provides n-ary systems, but it's the problem with the noise. And I will come back later. So we have introduced an entanglement, which is something weird, but indeed is the power lying under the quantum information. Why is so important entanglement from a communication perspective? Well, because we have the no-cloning theorem, which says that if you have a quantum information, an arbitrary quantum information, and you don't know the value of that quantum information, you cannot copy it. Full stop. So quantum information cannot be duplicated. This is the graphical pictorial representation of the theorem, of the proof of the theorem, which explore two properties, linearity and another property. I don't want to go into mathematical details, so I will skip the reduction of an absurdum. As you can see, the proof is very compact, very easily. Nothing hard here to understand, except the fact that we are not used to think about information as something that you cannot copy. So I want to stress first that quantum information cannot be copied. And second, that quantum information corrupts as time passes. So if you have a qubit and you want to preserve that qubit, preserving the qubit is very hard. Why? Because what is happening is the following, that the rest of the universe, that is usually called environment, interact with your quantum information. And as time passes, your quantum information will be destroyed. Now, this is a fundamental metric for exploiting quantum information. How hard is to preserve quantum information? Well, in this picture, you can see the IBM numbers, figures, and I want to stress out that the scale, the y-axis scale, is logarithmic. So this increment is a power law increment, which recall the Moore law. So we have an experimental law which dictates the progress of classical computation, which is universally known as the Moore law, which says that the power of your classical computer, well, decide the number of transistors that can be embedded in a certain space in a chip, but let's say the power of your classical computer double every 18 months. And here, when it comes to quantum information, we have something similar. The ability that our current technology has to preserve quantum information doubles almost every 18 months. And this is the reason why quantum information is becoming more and more mainstream, because we are moving from 1 picosecond at the end of the 19th century up to 1 millisecond nowadays. And 1 millisecond is a time long enough to starting to perform meaningful computation. Now, I will reply to the questions a little later during the talk. So let me summarize. We have quantum information, which differs from classical information for 3 reasons. We have superposition, which says that your qubit stores more information than a classical bit, which is good. Then we have measurement, which says that once you try to measure your qubit, you are destroying the quantum information stored in your qubit, which is bad. Then we have entanglement, which says that there are special states, multiple qubit states, so that when you interact one qubit, you actually are interacting with the second qubit at the same time. And if you change the first qubit, you are instantaneously change the second qubit, which, as we will see in few slides, is good. And then we have 2 problems. You cannot copy quantum information, and quantum information irreversibly collapse, or it's irreversibly altered by the environment as time passes. Now, quantum internet. We have several applications of a quantum internet which cannot be implemented in a classical internet. One of the killer applications of a quantum internet, even if it's not the most futuristic one, is secure communication. We say that when you measure, you destroy, and this principle is the underlying killer functionality of QKD. QKD exploits the measurement principle to implement a channel which is secure. Because when you send quantum information, if someone in the middle, an intruder, tries to read that information, he has to measure the information, so it destroys the information. And QKD schemes use smartly this measurement postulate to implement a secure channel. Then we have, and this is very important under the umbrella of the flagship, European flagship, which says that quantum internet must interconnect different quantum devices. We have distributed quantum computing. Now, let's first give you a hint of the power of quantum computing. With quantum computing, we have the following. This is RSA. This is integer factorization. This is the scheme underlying current internet cryptography. The current standards for internet cryptography use integer factorization. Why? Because this is the line. I'm moving through the line. Because it's very hard for a classical computer to solve this problem. So on the vertical axis, you have the key, the size of your key. So as long as you increase even a little the key of your encryption scheme, the problem becomes so hard that the best classical computer in the world will take more than the age of the universe, this is 1 billion years, to solve the problem. This figure is taken from one of my co-authors' paper, Rod Van Meter. So in 2005, actually this figure has been updated with the current classical supercomputing power. Let's suppose that we jump 30 years in the future from now. We take the best supercomputer that will be available 30 years from now, and you can see that still you just increase a small quantity, the key, the size of the key, and the problem becomes hard, intractable. The blue line is the power, the time required for a quantum computer to solve the same problem. And as you can see, quantum computer is almost insensible to this problem. It means that you can take an encryption key as large as you want, but if the quantum computer can easily solve your encryption scheme, so it can easily decrypt your password or your key in a few seconds. Now, this is the power of the quantum computing. What is the current problem? Why there is not yet a quantum computer able to solve the problem? Well, the problem is the current. The more qubits you put in the same chip, this is an IBM chip, a 2-qubit chips. If you zoom here, you will see in this point and this point the two the device is implementing the qubit, which is a superconducting capacitor. Let's call it a capacitor for ease of thickness. And this is the chip in and out connection. And this picture was taken in 2018 at IBM Zurich. They gave the chip to the participant to see in person. So we want to have a lot of qubits to have power, but the more qubits you put in the same device, the more noise there will be, because those qubits will start interact each other. So the solution, classical solution. What we do to have supercomputers? We interconnect different computers. We can do the same through the quantum internet. So we can have multiple quantum computers interacting with a quantum network. Why is distributed quantum computing so important? Well, for the scaling law, if you interact two classical computers, the virtual computer has the double of the power. So you add resources to the distributed computing architecture. The more resources you add, and your power grows linearly. When you talk with quantum computers, the power doesn't increase linearly, but it increases exponentially. And here you can see that by simply interconnecting two 10-qubit quantum processors, the volume of the power is several times larger. Actually, 1,000 larger of the power of 2 single devices. Is there any question about the distributed quantum computing slide? I saw that there are some questions about the correlation, and we will come back later. I don't think.
Does not look like there are any on that specific subject.
Okay. So, if this is a killer application, okay, let's simply take one of the existing classical protocol, change it a little bit, and implement a quantum internet. Well, we cannot do this. Why? Because we have the no cloning theorem, which says that you cannot duplicate information, and you have the measurement principle, which says that you cannot measure quantum information. And if you look at the basic strategies of the network layer protocol stack, you see that each and all the strategies assume that you can measure, you can duplicate information. For example, ARQ, what is ARQ? A strategy to counteract errors during the transmission of information. With ARQ, you send your information. If your information is corrupted by noise, you resend information. Well, with quantum information, you cannot transmit the same information multiple times. And why? Because you have the no cloning. So, to design a quantum internet, you cannot simply change some functionalities of your network stack. You need to redesign everything from scratch. And actually, entanglement is the killer ingredient to transmit quantum information. Why? Because thanks to entanglement, we have the quantum teleportation process. Quantum teleportation is, despite the name, is a process which allows you to transmit quantum information without violating the no cloning theorem. So you can transmit qubits without have to physically transfer the hardware storing your qubit, and without the violation of the quantum mechanical principle. What is the key ingredients of the quantum teleportation? You need to have an entanglement source. So the fundamental resource is entanglement. And then you need to send 2 classical bits. So this is the transmitter, qubits coming in, you use entanglement, and then you find your quantum information teleported at the destination. I don't want to go through the mathematical details behind quantum teleportation. They're not so.
Dr. Kalefi, there seems to be an issue with your audio. We've lost your audio. We've lost your audio. Give us just a moment. We are having some issues with the audio.
Can you hear me now?
Yes, we've got you now.
Perfect. And can you see the screen in a few moments?
The screen has not yet come up. Give us one moment. There's usually a delay on the... Okay, it has come up now.
Okay. I saw several questions about the slides. If you take note of this paper, in this paper, you will find all the material that has been presented during this presentation, and even more. Meaning that when we write this paper together with Angela Sara Cacciopoti and Lajos Hanso and Rod Van Meter, when we wrote this paper, we had in mind to provide a tutorial introduction to quantum information and quantum communications. Through the paper, you will find all the figures that you are seeing now in the slides with a better comment than the comment that I can give you in real time. Okay? So, of course, if is needed, I can share with Carrie this paper, but actually this paper is available publicly on internet. So just search for the title. Okay. Now, quantum teleportation, this is very important. We need to transmit classical bits. So when you think about a quantum internet, you should think about a network which exploits entanglement as resource to transmit quantum information and which operates together with a classical network. So there is no possibility that a quantum internet will replace completely the classical internet. Why? Because the classical internet is needed for quantum teleportation, so for quantum information. And here you see that entanglement is the underlying basis. You have a classical link, you have a quantum link, and you have, with this slide, you can see now we have done with the technical slides. You know, we are going back to more didascalic slides. You can see that you have a computing device which can implement different hardware technology, ion traps, quantum dots, superconducting circuits. You need the transducer to transduce the information, the physical properties stored in the hardware into photons, because nowadays everyone is looking at photons as the best carrier for quantum information. And you have the quantum network infrastructure that integrates the classical network, the classical internet, for transmitting classical information. And here you have a scheme where, again, entanglement is a big picture. Entanglement is the resource for quantum networks. And here you can see some experiments. Now, the important aspect of these slides is not the results within the slide, but the fact that we obtained these results through experiments with IBM Quantum Experience Platform. So, in the last 2 years, the quantum technologies are going out of the labs, and we, as engineers, should start working in the field. Now, what else? The agenda, meaning that one classical question is the following. If you look on the left at the equipment needed to implement a quantum bit nowadays, you can see that you need a full lab to implement a single qubit. So someone can question, is quantum internet to be practical? Will we ever have a quantum mobile phone? Well, this is not something that will happen in the next few decades. But if we look at the evolution of the classical internet, and if we look at the evolution of the classical computing, we can see a trend. Back in 1977, internet was just few laboratories interconnected. Now, in the next few years, quantum internet will be the same. Few laboratories interconnected with a quantum link. But we expect that the technology will mature, will grow, and sooner or later, we will have more and more quantum devices interconnected by quantum internet. And our vision is the following. We are at the stage where engineers should start working in the field, but with a joint work with the physics community. Right now, quantum technologies are an ongoing project, and you need an interdisciplinary approach to solve the problems. We need to work with the physics community to solve this challenging problem. And finally, I will close with this Twitter from Peter Sher, which is the inventor of the Scholl algorithm, which is the algorithm that allows a quantum computer to solve the integer factorization problem efficiently. When we say that with the Google Quantum Supremacy paper, the claims that quantum computers can possibly work are still coming, but he's very surprised because he say that the I will say the skepticism against quantum computing is a skepticism that finds its roots in the challenging that we are facing, not in the maturity of the technology. And I close this slide, and I welcome any open question.
Okay, we have a few questions here, and the first one that I'm going to ask is, this one comes from one of our audience members. It says, is the time for communication for teleporting the time for the EPR to share only?
Is the time for communication for teleporting? Well, no. Meaning that if the question was the time needed for teleportation, the time to accomplish a teleportation, is the time for sharing just DPR? No. You first have to share DPR, and this is something that you can do proactively, as long as the occurrence doesn't corrupt your information. So let's suppose that this doesn't exist, the occurrence. You first share entanglement, then whenever you need, you use entanglement to teleport the quantum information, but the process is not accomplished until you send the classical information. So this is the reason for which entanglement does not violate Einstein relativity, because entanglement is something that happens instantaneously, but indeed there is no transferring of information until you transfer classical information. And the transfer of classical information obeys to the relativity theory.
These next two questions, I believe, go back to your slide on combining quantum computers into a network. This one says, how hard is it to combine devices, as on the previous slide, in practice to get the exponential scaling?
Okay, so right now we have 50 qubits in one chip. So let's say that once you have the technology to implement a chip with 50 qubits, you can implement dozen, thousand of that chips. Because you have the technology to produce one, you can produce more. So our vision, but it's not just from my research group, but it's a vision shared by different research groups in the world, is the following. Let's interconnect these devices to scale the number of qubits. And the reason is the following. Once you move your quantum information from the chip to the photon, because at the end you are transferring information with the photons, you are preserving the quantum information very well, because photons, they do not interact very well with the environment. So to scale up the number of qubits, we have two possibilities. Either implement a photonic quantum chip, and there are companies and research lab trying to do that, or you interconnect quantum chips based on a different technology with photons.
Very good. The next question, again, follows the same one. How many entities can be mutually entangled? Only pairs, or can n entities be mutually entangled?
That's a very important question, because what it's called when you entangle several bodies, it's called multi-party entanglement, and you can do it. It has been done experimental. Actually, if you go to the IBM quantum experience and you play a little with their chip, you can entangle more than 2 qubits. But with multi-party entanglement, there are still basic fundamental questions open. And definitely multi-party entanglement is something that we should explore as IT community.
Okay, very good. This next one is, how do you achieve correlation between hardware and software? How does hardware respond to entanglement?
I will say that right now, there is no hardware and software, meaning that when we think software, we think, for example, to Java language programming or C++ or whatever we want. We are not yet at the level of having high-level programming. So right now, when you want to program a quantum chip, you work with gates. And actually, you create entanglement with gates. So there is a special gate, which is the CNOT, which allows you to create entanglement. Now, the job of the programmer is to smartly exploit entanglement for solving the problem. Can you hear me? I don't know if I lost my connection or is Carrie? Is Carrie not online? I will ask to the audience, can you tell me if you are listening to me, if my audio is coming fine or not? Okay. So we lost Carrie, if I understood correctly. To me, my audio is coming fine or not? Okay.
Marcelo, we can hear you.
We lost Carrie, if I understood correctly. I will try to...
Marcelo, can you hear me?
Yes.
Marcelo, we can hear you.
I will try to...
Marcelo, can you hear me?
Yes.
All right, well, I'll take over the Q&A for Carrie. Everyone, my name is Scott. I work with Carrie at Society. All right, next question. From a cybersecurity perspective, how early could we see impacts on secure transmission currently protected via classical crypto? And how should one approach securing and transmitting information going forward from an enterprise perspective?
Well, there is within the cybersecurity community the feelings that there are companies out there which are already storing encrypted traffic because they assume that sooner or later, let's say 10 years from now, they will be able to decrypt the encrypted traffic with the quantum computer. And so, for example, if you think to high-value information like embassies, communications, or something like that, there is the feeling that there are companies already recording the traffic to be encrypted later. And also, if this is not enough to convince you that encryption has to be reevaluated under the quantum computing risk, NSA already launched a call for post-quantum cryptography. So post-quantum cryptography is something that is still real within defense and highly security business models.
So thank you for taking over. I am back. I had a bit of an issue with my audio. So this next question is research in progress concerning viable quantum transport media preferable to photons?
Well, the problem with this topic is to catch all the news. So as everyone, I think everyone working in the research community, I have a Google Scholar alert. And the problem with the quantum networks right now is that there was a period 3 years ago that there was a Google Scholar alert every week, every couple of weeks. Now I'm having Google alerts every day, meaning 10, 20 new papers every day. So we should split. Physics community is already working on having chips interacting in a lab environment. This is something done. And this is from the physical community. From the engineering community, I want to, let me share something with you. For example, okay. I want to share the screen so that everyone can take note. Wait. Okay. Can you see this? Okay. I assume that you can see, for example, the Quantum Internet Research Group, which is a research group within ETSI, which is the Internet Engineering Task Force, which is working on defining protocols for the quantum internet. So we have a bottom-top approach from hardware to software, if you want to oversimplify, in the physics community. And we have also a top-bottom approach in the internet engineering community, which is saying, well, we will have in the next few years transmitter, receiver, link, and actually in our lab we are doing experiments in that way. So it's not something that it's only in few labs. It's, I would say, spread in different countries. Since in the next few years we will have transmitter, receiver, and link, let's work on the network protocol stack.
Are you ready for the next question?
Yes.
So the next question, I was asking this before I got cut off, so I'm not sure if you answered it or not. How does the system complexity change within qubits? And then it says form a practical implementation / realization perspective.
Well, if you have, as I said, usually a quantum system is intrinsically an n-level quantum system. If you engineer your n-level system to have just 2 levels, you can reduce the effect of the noise. The more your system increases in terms of levels, the more you are affected to the noise. So there is a trade-off. And probably it also depends from the hardware. So for example, in semiconductor technology, we are used to have just 2 levels, 0 and 1, due to the intrinsic characteristic of those hardware. If we change the hardware, we may change the number of levels, and we may find convenient to switch from a 2-level system to an n-level system. But this is an open research question right now.
Okay. This next audience member would like you to comment on quantum imaging.
I saw papers out there. I also got some papers in review, but I declined the review because I'm not an expert, honestly.
Okay, that makes sense. The next question is, how is the classical signal processing methods, how can they be used for quantum signal processing?
Wow. Okay. So this is an interesting question because at ICASP, so Signal Processing Conference, IEEE Signal Processing Flagship Conference, we try to give an answer to this question. So honestly, I'm very surprised that the quantum communications is an hot topic among network engineers, as you see the research group about queer research group that I showed you before. And instead, I feel less interest in the signal processing community. And I'm very surprised by this aspect for the following reasons. The limiting factor for quantum technologies is noise. The signal processing community has 50, 60 years of experience in fighting noise. So I think that sooner or later, the, let's say, anti-noise physical community, which works on quantum error correction, all of these aspects, will be taken over by the signal processing community. Because it's the signal processing engineers the best candidate to fight noise. And if you look at the anti-noise solutions or anti-noise algorithms that they are implementing within the hardware right now, I have the feeling that they are trying to fight the noise without the mathematical background that is needed to fight the noise. So I'm waiting to see the signal processing community jump in the field and find something clever that the physics community, due to their background, they cannot find. Or that's my guessing. I don't know.
Okay, very good. This next audience member has said, I just learned something new, which was that the need for keeping classical internet to have the quantum internet. Will, in that case, the concept of bandwidth change to the number of qubits passed along?
And the number of classical bits, yes. Well, let's say the following. We need to understand if if you are interested in networks, your main goal is to transmit information. Now, which kind of information do you want to transmit? If you want to transmit classical information, I think that using qubits is right now a nonsense. So let's say that we build a quantum internet. We spend $10 billion for what? For doubling the rate. Hopefully, if everything goes well, this is not the case. So whenever, for me, in the next 40 years, whenever you have to send classical information, you will use a classical network. If you have to send quantum information, then you need to use entanglement as your key metric. So I will be careful in saying that quantum bits, quantum entanglement will be the metric. It will be the metric only if you have to send quantum information.
Okay, very good. The next question comes in and asks, how do we keep entanglement when changing from a qubit representation in XYZ technology to optical information and back?
Well, when we start, okay, again, this is something that we start looking into the literature just for curiosity. As information engineers, we will assume, I think that for us it will be enough to have a certain fidelity of the transducer. So we are talking how can we convert superconducting quantum information into photonic quantum information, for example. Okay, there will be a transducer. And this transducer will have some parameters, and we will account for those parameters, for those key figures in our schemes, in our protocols. But we look into the literature to understand how this can be done. And the funny thing is that nowadays, one of the solutions to interact superconducting qubits with photonic technology is mechanical systems, like springs, very small springs, which is something very unfamiliar for us as electronic telecommunication information engineers. We are used to have digital equipment. it makes funny to think that in your computer, instead of your network card, which is all siliconic technology, you will have a very tiny spring connected with a mirror, and the tiny movements of the mirror will transduce superconducting quantum information to photonic quantum information. This is a funny thing for me. But I will say that the real answer is the following. It depends from the frequency of your domain. So for example, superconducting qubits, they work at microwave frequencies. So as long as your link can works with microwave propagation, you are good. So at the first step of the quantum internet, we will expect to have a couple of quantum chips in a quantum farm interconnecting among others. So the distance between computers in the first implementation of a quantum internet will be meters. And actually, physics community already interconnected quantum chips by using a microwave cable, which was 3 meters long, 9 feet, something like that. If you want to interconnect remote quantum devices, meaning a quantum chip in US and a quantum chip in Europe, then we need to wait the physics community to find clever, efficient way to convert microwave to optical length. Right now, the fidelity of these converters jumped in the last 3 years from 0.01, meaning 1% of fidelity of conversion, to 10%. So the increase in terms of performance of these converters is 1 order of magnitude in a couple, 3-4 years. So it's very good. It's very promising right now.
This next question, I believe it was asked while you were talking about the fact that quantum information in quantum system decays over time. The person is asking, will that destroy audit trails of information?
Wow. I think that this question is kind of an open research. Someone should write a paper about it. Honestly, I don't have any information about it. Let's say the following. Okay. We have the power of the quantum information, but we don't know yet which are the boundaries. After all, in the last 20 years, there were just a bunch of people working on quantum information, quantum programming. So it's a completely unexplored field. And as I said, for the signal process community, also the programming community is just nowadays start to look into the field. So I think that the more people will start to work in the field, and the reason for more people start working in the field is the money. I show you the first slides that you always need to follow the money, right? To understand the interest of the communities. So there is money in the field, more people will work in the field, and more opportunities, clever opportunities will come up. And I think that these questions deserve a research paper.
All right, very good. I think that's a good idea. This next person asks, have quantum computers been built with each of the quantum technologies you showed? Superconducting loops, trapped ions, quantum dots, etc.
Wait. Well, it depends. We should agree on the definition of quantum computer. So if we are thinking about a processor, a software interface, maybe 10 to 20 qubits, no. The top technologies right now are just 3, superconducting, ion, and photonic. For these 3 technologies, you have chips, you have software, and you have indeed a cloud access to these technologies. IBM, Xanadu, Rigetti are examples of players that allows you to use quantum computers based on these technologies. And indeed, since there is not yet a winner among these technologies, one of the open problems within the flagship European project, so there is money just to solve the problem, how will we interact different quantum technologies? This is an open problem, and it's important for two reasons. First, because there is no winner among technologies, so in the next decade, in the next 10 years, we will see different technologies working, and we should find a way to interact them so that the money and the effort spent in each technology will not be wasted. Secondly, let's think about computation. When you think about computation, you want something that can change fastly. Why? Because the power of your computation is the clock. So you want something that you can change quickly, so that clock will be higher. But the quickly your technology allows you to change the qubit, the more interference you have from the environment. So you may have the following scenario. You have a technology for computation. Then you have a technology for memorization, because memorization have the opposite constraints. You want something that changes very slow with the time, because you want to preserve information. So you have a technology for computation, you have a technology for memorization, and then you have technology for information transmission, which are photons. And if you think about this scenario, you need to interact different technologies within the same quantum computer. So we have two research goals. Having different quantum computers, meaning different computers with different technologies, interact each other. Big scenario. And then you have a smaller scenario, smaller in terms of size, not importance, having different quantum technologies interact each other within the same quantum computer.
Okay, very good. We are quite a bit over our time, but I'd like to take these last two questions here. This next question, as somebody who's much more interested in the theoretical elements of quantum mechanics, it appeals to me. So I'm going to read it next. As a practicing engineer, do you have any thoughts on quantum foundations? E.g., how to differentiate between different interpretations of quantum mechanics, such as Copenhagen versus transactional versus many worlds, etc.? And if you prefer Copenhagen, what do you believe is the role of the observer?
Honestly, I'm very fascinated by as I think everyone that approach quantum mechanics, I'm very fascinated by the many world interpretation. But I have to be honest. When it comes to the interpretation of the quantum mechanics, I feel like I can see a kid in front of a computer. When you put a kid in front of a computer, he starts using it. He doesn't care so much about how the computer works, but they are good to use the computer, right? Or the iPhone or whatever. So my approach to quantum information is the same. There is this fascinating device for me, which is quantum information. And I'm trying to use it, starting using it. Of course, I try to read, to study, but still, I want to use it. And I leave to the philosophers or to the people smarter than me, which are them. There are, of course, thousands, especially in the quantum mechanic theorist community, leave these big questions. I just want to tell this. There was a presentation in which we were giving a tutorial, and there was people questioning the linearity of the quantum mechanics. So I think that we as engineers should step back and say, quantum mechanics for us is a toolkit. We use it, but we don't need to fully understand it. In the same way in which, for example, programmers nowadays, they are programming computers, but they are not an expert in terms of hardware, CMOS, or transistor design.
So in other words, you tend toward the shut up and calculate idea, right?
Wow, that's the sentence that we use in our class. I didn't want to use here because, but yeah, that's my style.
Okay, this last question before we go is the satellite entanglement demonstration and others have transmitted hundreds of kilometers. Thoughts on this?
Well, we should understand the following. As everyone, when you write a paper, I don't know, there are like this picture on Twitter that you have an abstract which is like this, and then within the paper you are like this, meaning that the satellite missions was an incredible experiment which attracted a lot of attention and it opened a new field. But we are still trying to have point-to-point communications. And if you are practical with network, you know that among the 5 layers, 7 or 5, it depends if you use OSI or TCP/IP framework, you have 4 more layers to design. So the satellite experiment was just this to me. Hey, people, we may use fiber links and satellite links. And the reason for using satellite links, which are very expensive and you usually don't use for classical information, is that at the present technology, satellite links gives you a larger range with respect to fiber links. But to me, you need to interact fiber and satellite links. That's, to me, the key to implement a quantum network. So satellites are part of the picture, not just the picture.
Okay, very good. Dr. Kalefi, I'd really like to thank you for your presentation today. It was fantastic. I enjoyed it. I'm absolutely certain everybody else enjoyed it, especially given how many questions we had. I'd like also to thank everybody for attending. You guys have been great. The questions you've presented are wonderful. I want to remind all of you that on October 16th and 17th, the Distinguished Visitors Program and Student and Young Professionals Committees will be hosting a virtual conference on cybersecurity, where we have a number of great speakers discussing topics such as graduate programs in cybersecurity, security of cyber-physical systems, advancements of information security algorithms, dealing with a cyber attack, access control in a touchless society. The keynote is going to be at 12 o'clock U.S. Eastern Time on the 16th, and that will be presented by Stefano Zanero, Associate Professor at Politecnico di Milano, titled Crouching Tiger, Hidden Robot, Removing Fear from Cyber-Physical Security. In addition to the Distinguished Lecturer webinar series, we also have the Build Your Career webinar series that focuses on business soft skills such as communication, presentation skills, career transition, interviewing tips, among others. Our next Build Your Career webinar will be on the 21st of October at 11 a.m. U.S. Eastern Time on Writing Confident, Efficient Emails by Elsa Velasco-Paul, founder of the M&E Group. Registration is now open, and we will be sending you a link to these future events along with the recording of this webinar, and I will also try to put in the link to Dr. Kalefi's and Dr. Cacioppuoti's article with that, so that you guys will have access to the information that has been given. So again, thank you, Dr. Kalefi. It has been great. We've enjoyed it.
Thank you to everyone.
Bye.